Hello students, welcome back to my YouTube channel Chemical Funda. In today's video, we are going to see particle nature of electromagnetic radiation. From that, Planck's quantum theory we will see in this video. There were some relationships that were not able to explain by electromagnetic theory of 19th century, which is also known as classical physics. So we will see certain points and certain concepts that was unable to explain by the classical physics. First one is the nature of emission of radiation from hot bodies. It is also known as black body radiation. Next concept is of ejection of electrons from metal surface when a radiation strikes it. That effect is called as photoelectric effect. Next concept was variation of heat capacity of solids as a function of temperature. And fourth one was line spectra of atoms with spatial reference to hydrogen. So this phenomenon indicates that the system can take energy only in discrete amounts and all the possible energies cannot be taken up or radiated. So the first concrete explanation for this phenomenon of black body radiation mentioned above was given by Max Planck in 1900. Hot bodies or hot objects, they emit electromagnetic radiations over a wide range of wavelengths. So if you will see any hot body, it emits electromagnetic radiation over the wide range of wavelength. And at higher temperatures, an appreciable proportion of radiation is in the visible region of the spectrum. So when we are increasing the temperature, that radiations comes under the visible region. As the temperature is raised, as the temperature is increased, a higher proportion of short wavelength, that is blue light, is generated. If you will take an example of iron rod, when this iron rod is heated in a furnace, it first turns to dull red color. Then progressively it becomes more red. And when we are increasing the further temperature, then it becomes white. It glows and it becomes white, and finally it becomes blue. So it means that as the temperature is increases, a higher proportion of short wavelength, that is blue light, is generated. We can observe from this graph as red radiation is more intense at a particular temperature. Suppose that temperature is T2, and blue radiation is intense, or it is more intense at another temperature. That temperature is T1. Intensities of this radiation of different wavelengths emitted by hot body depend upon its temperature. So their intensities are different for the different temperature and different wavelengths. When the surface of an object is irradiated with light, is nothing but electromagnetic radiation, a part of radiant energy is generally reflected, some part is absorbed, and a part of it is transmitted. It means that whenever any object is irradiated with light or electromagnetic radiation, all the energy cannot be absorbed or cannot be emitted out. The reason for this incomplete absorption is that ordinary objects are, as a rule, imperfect absorbers of the radiation. They are imperfect absorbers. Then which substances are the perfect absorbers? Yes, black body. Black body is an ideal body which emits and absorbs radiation of all frequencies uniformly is called a black body. So black body is a body or is an ideal body that emits and absorbs radiations of all frequencies, and the radiation emitted by such a body is called as black body radiation. So this is black body radiator. The radiation emitted by this body is called as black body radiation. In practice, no such a body exists as a black body, but carbon black. Carbon black approximates fairly closely to the black body. So if we will see the physical approximation to the black body, so it is a cavity with a tiny hole which has no other opening, and any ray entering in the hole will be reflected by the cavity walls and will be eventually absorbed by the walls. What it means? This is a cavity with a tiny hole and it has no other opening except this one hole, and all the radiation incident in this cavity is get absorbed by the wall, and all the radiations are reflected in this cavity and finally they absorbed by the wall of this black body. So in a black body, the emitted radiation is only a function of radiator's temperature, because all the incident radiations are absorbed and emitted radiations are only the function of radiator's temperature. So for a black body, the amount of light emitted from a black body and its spectral distribution depends only on its temperature. So temperature is a function over here. For any black body, at a given temperature, intensity of radiation emitted is increases with increase of wavelength. Then it reaches to a maximum value at a given wavelength and then starts decreasing with further increase of wavelength. So if you will take any black body, as we are increasing the temperature, the intensity emitted is increases, then it reaches to the maximum value and then it starts with decreasing with further increase of wavelength. So this is for a black body. First its intensity increases, it reaches to the maximum value and then it starts decreasing. And it is true for the all temperature. So here we can observe, as we increase the temperature from 3000 to 7000 Kelvin, this peak of the maxima, it shifts towards the left, that is towards the less wavelength. So increase of intensity with temperature and decreases the peak of wavelength with temperature. So that can be observed from this graph. So this is the wavelength and intensity relationship. When temperature is increased, here T2 is the higher temperature than T1, maxima of the curve, it shifts towards the lowest wavelength. So as we have discussed, as the temperature increases, the maxima of the curve shifts to the short wavelength. So Max Planck arrived at a satisfactory relationship by making an assumption that absorption and emission of radiation arises from oscillator, that is atoms in the wall of the black body. So these atoms in the wall of black body, they are absorbing and emitting out radiations in the form of oscillator. Then Max Planck assumed that these radiations could be subdivided into discrete chunks of energy, discrete small packets of energy. This radiation could be divided, and he suggested that atoms and molecules could emit or absorb energy only in discrete quantity. And atoms and molecules, they are not emitting or absorbing energy in a continuous manner, but they are absorbing or emitting out radiations and energy in discrete quantity, in individual quantity. And he gave the name quantum to the smallest quantity of energy. The smallest quantity of energy is known as quantum, and that can be emitted or absorbed in the form of electromagnetic radiation. So quantum is the smallest quantity of energy that can be emitted out. So the energy E of a quantum of a radiation is proportional to its frequency, and it is expressed by the equation E is equal to h nu. Here E is the energy, h is the Planck's constant, and it has value 6.626 into 10 raised to minus 34 joule second, and nu is the frequency of radiation. With this theory, Planck was able to explain the distribution of intensity in the radiation from black body as a function of frequency or a wavelength at different temperatures. Then next is the concept of quantization. So what is quantization? Quantization means the energy can take only one of the values from the following set, but it cannot take on any values between them. So energy can take either any of these value, but it cannot take any value in between these two. So in between these h nu and 2h nu, or 2h nu and 3h nu, energy cannot take any value in between these. So this is the explanation by the quantum theory as compared to classical theory for the energy of the radiation. So this quantization has been compared to standing on the staircase by the Max Planck. Any person can stand on any step of the staircase. So any step of the staircase that person can stand, but it cannot stand in between these two staircases. Then after this, there was an equipment for studying the photoelectric effect, that is light of particular frequency. It strikes the clean metal surface inside the vacuum chamber, and as soon as this light is irradiated on this metal surface, electrons are emitting out from this metal surface and they fall on this detector. So these ejected electrons from the metal are counted by detector, and it measures the kinetic energy of these ejected electrons, and the current is measured by using the ammeter. So this quantum theory was given by Max Planck. He was a German physicist. He received his PhD in theoretical physics from the University of Munich in 1879. In 1888, he was appointed as director of the Institute of Theoretical Physics at the University of Berlin. Planck was awarded the Nobel Prize in Physics in 1918 for his quantum theory, and this Max Planck also made significant contributions in thermodynamics and other areas of physics. So this is all about Max Planck and his quantum theory. In next video, we are going to see photoelectric effect. So students, thanks for watching this video. Thank you.